So in this subsection, subsection 2.5, we're going to start proving some things about probability. It's proving certain properties that this probability function, this p with all the double lines on, what properties it has. Now, before we start, we've got to set up the rules here. The rules are the only things we're allowed to use are the three axioms and, basic mathematics and logic. We can't say it seems common sense that, or it seems likely that, or it ought to be the case that. We've got to go from just the three axioms. Those are the only things we're allowed to use to prove our properties. So, as a reminder, these were our three axioms here. The first one, that probabilities are non-negative. The second one, the probability of the whole event is 1. And the third one, this thing with the disjoint unions, adding them up. So, here's some of the properties that we're going to try and show here. I've listed 4 properties of probability that we might want to prove. There'll also be a 5th one in the next subsection that's so important I gave it its own subsection. So the first of these is that the probability of the empty set, the probability that nothing happens, is 0. The second one is telling us something about the probability of A not happening. It says the probability that A doesn't happen is 1 minus the probability it does. This third one says that if B is a subset of A, then the probability of B is no bigger than the probability of A. That is, if when B happens, A always happens, then A's probability is at least is bigger or equal to the probability of B. And the fourth one says that probabilities are between 0 and 1. That's definitely something we think ought to be true. We're going to prove this from the axioms. So, let's have a go at trying to prove these. Well, for statements 1 and statements 2, I'm going to put those on the problem sheet for you to have a go at yourself. Now I'm going to do numbers 3 and 4 to give you an idea of how we go about these things. Now, usually, the key with these proof from the axioms problems is try and find a disjoint union somewhere. Because once you've found the disjoint union, you can use axiom 3, right, that says the sum of the probability of the union is the sum of the probabilities, and then we're all in good place. So the trick with these kind of things is try and find a disjoint union somewhere and apply it. So for number 3, let's draw a picture of what's going on here. We've got our set omega, we've got our set B, and we've got our set A. And B is a subset of A, so B is a circle inside A. It's not like they're interlocking circles like we had before. B is inside A. So what would be nice would be to write A equals B union something, and we'd like it to be a disjoint union, right? Because then axiom 3 would give us a statement that connects A and B, and we'd be in with a good chance. So B is this bit in here. So if we want it to be a disjoint union, then what we want is this bit around here that's A, but not B. Right? Because then that, together with B itself, would make up A as a disjoint union. So what we want there is the bits of B, bits of A that aren't B. That's A and not B. Right? That's what the thing I've shaded in blue there is. It's all the stuff that's in A and intersection, not complement in B. A intersect B complement is the stuff that's in A but not in B. So very, very crucially, it's a disjoint union. So that means that we can use axiom 3. And axiom 3 says the probability of a disjoint union is the sum of the individual probabilities. It's the probability A equal to probability B plus probability A intersect B complement. We wanted to show that the probability of A was bigger than or equal to the probability of B. And we've got it's equal to probability of B plus something. So if we can show that that something is greater than or equal to 0, then we're done. But look, this thing is greater than or equal to 0 because it's a probability. And Axiom 1 told us that all probabilities are greater than or equal to 0. So that means that the probability of A is equal to the probability of B plus something positive. So probability of A is greater than or equal to probability B. And that proves statement number 3. I've written a little square there in the margin. A little square is what we often write in mathematics to say that we've proved the thing we're trying to prove. And there we've proved the third statement by using Axiom 1 and Axiom 3 by finding ourselves a disjoint union. And so when you try and solve numbers 1 and 2, you're similarly going to want to seek out a disjoint union like that. Statement 4. Note that statement 4 had 2 parts. The first part was probability of A is greater than 0, and the second part was the probability of A is less than 1. So let's do those separately. Probability A greater than or equal to 0 just is Axiom 1, so there's nothing to prove there. What about showing that probability of A is less than or equal to 1? Well, so for some event A living in omega, we can use part 3 that we've just proven, right? Because that told us about what happens with subsets. Right? It said that if something's a subset of something else, then the probability is smaller. So that tells us the probability of A is less than or equal to the probability of omega by the thing that we've just proven. But probability of omega, that's axiom 2, right? Axiom 2 tells us that's equal to 1. So probability of A is less than or equal to 1 also. And we're done with the fourth statement. So there we used axiom 1, axiom 2, and the thing that we just proved, which itself used axiom 1 and axiom 3. So look how we're knitting together just these axioms and nothing else to prove these statements. The next thing we're going to show is so important that I've given it its own subsection and its own video.